Hello, my name is Rain Islam, and for the grand challenges for engineering, my group and I have decided to go with the topic, provide access to clean water. So after reading through this section, a few things stood out to me. Number one quote specifically was, lack of clean water is responsible for more deaths in the world than war. Also, about 1/6 people today do not have access to clean water. In the US, we take a lot of things for granted, whether it's being able to go to your local fast food place or get coffee at Starbucks. Water is something that we all take for granted. In terms of issues related to unclean water, there's many diseases that's correlated to diarrhea. And in terms of water is usually very abundant, but location is the biggest issue. And to put water consumption in perspective, household water usually accounts less than 5% of total water used. Also, most of the water consumption is used in agriculture and the industry. So as engineers, our goal is to solve issues. And many engineers around the world, they came up with a few solutions in terms of solutions to clean, usable water. One solution was desalination. Essentially, desalination is to extract salt from seawater, which ultimately becomes drinkable and usable. And modern day desalination uses reverse osmosis, which essentially uses a membrane to separate the salt. The only problem with this method is desalination plants are very expensive to build and require lots of energy to operate, and this method is only suitable for rich countries along the seaside. So through desalination, there's a new upcoming approach called nanoosmosis. Comparing nanoosmosis to desalination, nanoosmosis uses less amounts of energy and costs less. They're still very similar to their approach, but nanoosmosis filters out the salt with the use of tiny tubes of carbon. These tiny tubes are nanotubes, and their size and scale is in the use of nanometers, which ultimately means it's a much more thorough filtration system. But desalination alone cannot solve the world's problems. So, other than desalination, what other technologies will provide clean water? One way we can provide clean water is to improve recycling of wastewater and sewage treatment, so the water can be used for non-personal uses such as irrigation and industrial purposes. Also, if we simply reduce our water usage, that could increase our total water in other parts of the world. Developing countries alone, irrigation uses about 80% of their total water use. And one method is through dip irrigation, as you can tell in this picture here. Dip irrigation simply reduces the agricultural water demand. The problem with dip irrigation is it's not a perfect solution for plant growth, and it does not provide enough water to cleanse the soil due to the water loss. So ultimately, this is an inefficient long-term solution. Another alternative method in terms of reusable clean water is small distillation units. This is much more attractive to those where infrastructure and distribution problems are more severe. This solves most issues in rural and low-income areas, but once again, this is still not going to solve the world's issues in terms of unclean water. So, to sum up everything as problems as a whole, clean, cheap water is available to the rich, but the poor have to seek out supplies at much higher costs. Now to discuss the article that my group and I have found. The article's name is Mortality and Water Hardness. They analyzed data in 61 cities in England and Wales, analyzing mortality and drinking water hardness. More specifically, water hardness related to calcium concentration. In their data, they analyzed 61 cities, but we decided to only analyze 52 because there was an uneven amount of cities in north and south, and 26 in each region. The average mortality rates were about 100 male inhabitants, and the calcium concentration were in parts per million. Essentially, their data sets were from 1958 to 1964, and ultimately they were looking for if there was any correlation with calcium concentration and mortality rates linked to that. Now to show you the data sets. So originally, this was the data set from here. all the way to the bottom, and this will split up to north and south. We decided to go with hardness versus mortality rate, so we split them up into smaller groups so we can easily manipulate the data into MATLAB. So now I'm going to be talking about a little bit of the functions that my group and I decided to use. We decided to use the menu function, and the reason behind this is because we wanted to split it up into north and south, and this simply just aided us into that. Also, the if and else statements supported the menu functions, so if you wanted to choose, let's say north, it would show us all the input values and variables regarding to that. And polyfit created a trend line which showed an average amount of water hardness compared to mortality rates. So now I'm going to discuss the algorithm that my team and I have produced. We began our algorithm by collecting data on water hardness and mortality. From there, we organized our data points between north and south of England and Wales regions. And then we had a bit of a dilemma. We didn't really know what to do with our data points. So after discussing upon each other, we came to agreements where we create a menu function. The reason we created a menu function is to further analyze north and south regions of both England and Wales. If the user chose option 1, which was north, they would be represented by a graph showing the relationship between water hardness and mortality, and vice versa for if the user chose south. After that, we export the data from Excel in order to plot the data points, and then we created a trend line using polyfit to exemplify rising mortality rates along with hardness of water for both north and south plots. And finally, we used the data together with graphs to demonstrate the possible correlation between mortality hardness of water and evident reason to provide access to clean water. And finally, I will now discuss our code in MATLAB. We begin by giving a brief description. We will analyze the mortality and drinking water hardness averaged over the years of 1958 to 1964 in the north and south regions of England and Wales. And the data, or this data, was over male death rates in 52 large towns, and more specifically 26 cities in the north and 26 cities in the south. So of course we begin our code with TLC, clear all, and close all. From there, we implemented the menu function, which gives the user the option to choose to analyze the water hardness and mortality rates in the north or south of England and Wales. From there, if the user chose option 1, which was north, we would import our data, and then we'd have to transpose it in order to manipulate it easier. And after that, we wanted to sum up the totals and total hardness along with total mortalities. The reason we did this is so we can further manipulate the data to give the user more information. And the total amount of cities in the north was 26, and we decided to fprint the total amount of cities in the north so the user has more information. From there, we decided to take an average by putting the total hardness in the north over the total cities. And we decided to fprint as well. Total average amount of water hardness, total amount mortality rates. And of course, we had to plot the data in our graphs. So we create a figure, plot, title axis, X labels, Y labels, grid, hold on. And of course, we have to next polyfit in order to give an average for both data points. And to finalize the north, we had to create an sprint to create a y equals mx plus b trend line. In terms of the southern region, we essentially did the exact same thing as we did previously in the northern region, but just changed a few variables. So I'm not going to be going over that. And since we created a menu function, we had to do an if and else, and to end it, we just used the end function. And at the end, we decided to create another menu function. Essentially, we wanted the user to have a little bit more interaction while they were running the section. So we asked the user, does this data represented in the graph show a correlation between the mortality and water hardness? If they chose yes, they'd be given another prompt. If they chose no, they'd be given another as well. If they chose yes, correct, the data indeed does show a correlation between water hardness and mortality rate in these towns. And if they chose no, incorrect, the data does not show a correlation. If you're having trouble seeing this
please go back and rerun the code. I will now run the code. The first thing that it comes up is the prompt. Choose to analyze water hardness and mortality rates in North or South England and Wales. If I choose North, I'll be given this graph. And as you can tell, the water hardness progressively increases, and as the water hardness increases, there seems to be an increase in death rates as well in the northern region. In the command window, we are given the total number of cities in the north, which is 26, the total average amount of water hardness, which is 32, and the total average of mortality rates, which is 1647. And another prompt is also brought up. Does the data represented in the graph show a correlation between mortality and water hardness? There seems to be a correlation linked to water hardness and mortality rates, so we choose yes. There is a correlation. If we chose yes, we are given in the command window, correct, the data indeed does show a correlation between water hardness and mortality rate in these towns. Now I want to rerun this code and view the southern region. I choose south, and once again I'm given the total number of cities in the southern region, which is 26, the total average amount of water hardness, which is 70, and the total average amount of mortality rate, which is 1377. Once again, as you can tell, progressively, as water hardness increases at 140, we can tell that the average mortality rates also increases in the southern region. And like I mentioned before, if I hit yes, I'll be given a prompt, but this time, just for demonstration purposes, I will hit no. There is not a correlation. If I hit no, a prompt will be given, such as incorrect, the data does not show a correlation. If you are having trouble seeing this, please go back and rerun the code. Now to sum up all the information that we collected. As you can tell in both graphs, in the northern and in the southern regions of England and Wales, as water hardness increases, there seems to be a direct correlation with average mortality rates also increasing. This means that if we can somehow filter out the calcium within the water, there might be a drop in the average mortality rates. And ways to do so is to simply do, as I said previously during the introduction, such as possibly desalinating the water, but instead of removing the salt, we could rather remove the calcium concentration. Another option is to keep the water the way it is, but simply implement distillation units. If we implement distillation units throughout the northern and southern regions, there might be a drop in the average mortality rates.